Production of radionuclides. Types of radiopharmaceuticals. Types of radiopharmacies. Academic, medical schools, hospital-based, make their own drugs for use in only their area. Centralized, Cardinal Health or GE. Advantages of centralized pharmacy. The limits exposure to employees, performs all QC. Radiopharmaceuticals are delivered and ready to use. Nuclear pharmacies can buy in bulk and pass the savings on to the patients. Disadvantages of centralized pharmacy. There's a delay of up to 2 hours for delivery. If you have a large volume of patients, it can be more cost-effective to have your own generators and compound your own radiopharmaceuticals. Who regulates the nuclear pharmacy? Federal Drug Administration, the FDA. State Board of Radiologic Health. Department of Transportation, DOT. Nuclear Regulatory Commission is the NRC. 4 ways to produce isotopes: reactors, accelerators, cyclotrons, and generators. Reactors allows for controlled nuclear reaction, constructed with fuel rods made by fissile materials like uranium-235 and plutonium-239. Fissile is a material that is capable of sustaining a chain reaction. Fuel nuclei undergo spontaneous fission. Fission is the breakup of heavy nucleus into 2 fragments of equal mass, accompanied by the emission of 2 to 3 neutrons with a mean energy of 1.5 MeV. Heat is usually released about 200 MeV, which is removed by heat exchangers that produce electricity in the nuclear power plant. Neutrons are usually emitted in each fission, which can cause further fissions to occur, leading to a chain reaction which will ultimately cause a meltdown. To control the chain reaction, excess neutrons are removed by cadmium rods in the fuel core. Water, beryllium, or graphite are usually distributed in the spaces between the fuel rods. They're called moderators. Moderators allow the neutrons to become thermalized or slow down. There are 2 types of reactors. Power reactors, which convert the heat generated from fission process into electricity. Isotope production reactors have specialized ports where target material is introduced, causing neutron activation of stable nuclides into radioactive nuclides. There are 2 types of reactions: fission and neutron capture, or neutron activation or irradiation. Fission. Materials with an atomic number greater than 90 can go through fission because they have higher energy. It will give off 2 lower atomic number products. These products are collected and chemically separated. The most common target used in fission for radionuclide production is uranium-235. In fission, we are changing the substance completely, not just adding a neutron. This makes the materials carrier-free. Common fission-produced radiopharmaceuticals are iodine-131, molybdenum-99, and xenon-133. Neutron capture activation. This is the method for production of lower energy isotopes. The process involves capturing neutron states by a stable nucleus. It undergoes spontaneous fission. Then it interacts with the other materials in the reactor, thereby causing a chain reaction. This is controlled by using a neutron-absorbing material like cadmium around a fuel core. These are the rods. These neutrons will react with various substances, forming radiopharmaceuticals. In order to make the neutrons more useful, they are slowed down by the use of water, deuterium, graphite, or beryllium, also known as moderators. So what is happening is that the thermoneutrons hit the material and are absorbed into the nucleus. This creates an unstable radioactive nucleus of the same chemical identity as the irradiated material. What this is can be determined by the energy in the half-life. The problems are we don't usually get a pure product. There are carriers, which are a detectable amount of stale element. What can we do to reduce the carrier? Start with an enriched product, or let the elements with the shorter half-lives decay away before use, or remove the materials called bachelor by using precipitation, distillation, chromatography, or conversion to gas. On page 23 in your book, look up the following half-life, energy, mode of decay for the following. Specific activity. Radioactivity per unit mass of a radionuclide. An example is 100 milligrams of iodine-131 containing 150 millicuries. The specific activity would be 100 or 1.55 millicuries per milligram. Specific activity versus concentration. Concentration is the radioactivity per unit volume of the sample. If carrier-free radionuclides, specific activity is related to the half-life. The specific activity is equal to 3.13 times 10 to the 9th over the mass of the number of the radionuclide times the half-life. Accelerators. A stable nucleus is bombarded with charged particles and ions and are accelerated along a linear path using electricity. Commonly used accelerator produced radioisotopes strontium-82 and cobalt-57. Generally, accelerators are used to produce higher isotopes. Part 2. We will now discuss the last two methods of isotope production, cyclotrons and generators. A cyclotron is charged particles are accelerated in a circular path called Ds A and B under vacuum by means of an electromagnetic field. The charged particles moved under a magnetic field with gradually increasing energy. The larger the radius of the circle, the higher the energy of the particle. When targets of stable elements are irradiated with an external beam of accelerated particles, the particles irradiate the target, causing a nuclear reaction. The nucleus with excitation energy is formed and disposed of by emission of nucleons. Particle emission is followed by gamma ray emission. Radioisotopes produced by a cyclotron are thallium-201, indium-111, gallium-67, iodine-123, carbon-11, nitrogen-13, oxygen-15, and fluoride-18. Radionuclides produced by cyclotrons are usually neutron deficient and therefore decay by beta emission or electron capture. An example of a cyclotron is indium-111 is produced by irradiating CD-111 with 12 MeV protons in a cyclotron. The nuclear reaction is called CD-111 P(N) indium-111, where CD-111 is the target, P the proton is the irradiating particle, N is the neutron, is the emitted particle, and indium-111 is the product radionuclide. The excitation energy will be dissipated by gamma ray emission. Please note that the radionuclides produced with the atomic number difference from those of the target isotopes theoretically should not contain carriers. Generator systems. Devices for separating a short-lived isotope from a long-lived isotope. A generator uses the principle of a parent and daughter. The parent isotope is a longer half-life. It will decay into the daughter. The daughter will be collected, and that is what's used. Moly-to-Tech generator systems are most commonly used in nuclear pharmacy. Parts of a Moly-to-Tech generator are saline source, the Moly column, 0.22 micrometer filter, and a collection vial. Here we have an image of the generator with the eluting solvent up top and the air vent up top, and inside is the adsorbent material followed by the filter, and then attached up top is the evacuated collecting vial. So A is going to start with the eluate. It's going to go down and through the adsorbed parent activity, and then through the filter and up into the collecting vial, which is the daughter activity, and it's all, the parent is all covered by that lead shield. Sub-definitions. The eluate or elution is the solution that is taken from the generator. Elude means milking the generator. Cow is the generator. Pig is the lead containers for radioactive materials. The cross-section of a generator. Here we pretty much see the same thing. Yeah, it's pretty much the same thing, just from the other side. And we get a little bit detail of the column on the right-hand side. A wet column and a dry column. The main differences between the wet column and a dry column generator is the location of the saline. In a wet column, it is inside the generator. The column is continually bathed in saline. In a dry column, it's not part of the equipment. Dry is better due to the idea that water can cause radiolysis. Therefore, there is less chance of free radicals developing, which will interfere with the tech chemistry. On the left side, we have a dry generator. On the right side, we have a wet generator. And as you can see, the eluate on the left side is in the top left and outside of the generator. On the right-hand side, you see the eluate is built into the inside of the generator. Different types of generators. Rubidium to krypton. Krypton 81 was used for years in lung ventilation studies. Instead of saline, it used oxygen to take the krypton off of the rubidium column. It was then delivered to the patient and is inhaled. Generator advantages. They have better images, can take same views as with perfusion. They have short half-life of 13 seconds, therefore less exposure. Disadvantages, you must get a new generator every week, and it was very expensive. Tin and indium generators. This used hydrochloric acid to take the indium 113M from the column. It's a long-lived generator. It will last up to 6 months, but the indium 113 is not a good radioisotope. It's mostly used in poorer countries. Strontium 82 and rubidium 82, used for PET cardiac perfusion imaging and uses normal saline to elude. Germanium 68 and gallium 68. Germanium 68 is used to calibrate PET equipment, eluded by EDTA. The yield of TEC. Activity of TEC when transient equilibrium between moly to TEC is reached by the amount of TEC is equal to 0.957 times the amount of TEC to time. For example, a 2.6 curie moly generator calibrated for Wednesday noon was received on Tuesday before. What would be the total TEC 99M activity eluded at 8 a.m. on Friday? The solution. The moly activity on Wednesday at noon was 2.6 curies. So the moly activity at 8 a.m. on Friday, when doing the decay method, you get 1.64 curies. So the TEC activity is going to be 0.957 times that 1.64 curies. That equals 1.57 curies. The end.